Good morning, shout. Please stand for the Pledge of Allegiance. I pledge allegiance to the flag of the United States of America and to the republic for which it stands, one nation, under God, indivisible, with liberty and justice for all. Now for the Texas Pledge. Honor the Texas flag. I pledge allegiance to thee, Texas, one state, under God, one and indivisible. Now for a moment of silence. Teachers, please take attendance now. Your message from Healthy Shout. Find a creative outlet, whether it's drawing, painting, photography, or dance. Having a way to express yourself creatively is a great way to keep your mind healthy and happy. Student council elections are taking place. Learn about your candidates at elections.westlakestuco.com and check your email for this year's voting form. And for the first time in school history, Westlake basketball is headed to the state championship game. The Shout will play at the Alamo Dome this Saturday. Get your tickets now. Check Westlake Nation Twitter for more information. Go Shout!
Okay.
Are you going to be posting the answers to problems at 8?
I did like 30 minutes ago. So I just did that, yeah. All right, so we are doing lesson number 20. Tomorrow is a tutoring day, so you'll check in like we normally do on a Thursday. It's been a while since we've had a normal Thursday, I feel like, but what's up?
I'll be here for that.
Okay. So normally you'll check in tomorrow, then you'll you can work on your problem set, which is due Friday, which has these two lessons, yesterday's and today's on it. I posted the answers to those last period. So if you're needing to see the answers to check your work, that's there. And then Friday we'll have a lesson, which won't be on a problem set until after spring break with some other lessons. So it's not like it's due right after spring break. You'll have a little bit of time there. And then I guess that's it. Oh, I knew that was going to happen. All right, hold on. Let me check another person in here. Once I've started sharing my screen, it's kind of a pain. So today we're doing what are called eigenvalues and eigenvectors. Definitely a part of just about any college linear algebra course that you would ever see. Eigen, I think, means same in German or something like that. Is where it comes from. Yeah. Does it really? I thought I remembered that, but I couldn't remember. All right, so most vectors change when you multiply by a matrix. So we've been doing this now since the beginning of the semester. You take a vector like my little blue one there, 1, 2. I multiply by a matrix, I get another vector. Okay, and generally if you just picked a random vector and a random matrix and I multiplied, I will get a new vector going in a different direction, meaning not parallel, right? Those two are not running in the same direction. 1, 2, and 5, 7 that I get here. So generally, if you were just to pick a random vector or random matrix, multiply, you'll get a new vector going in a different direction. There are a special class of vectors called eigenvectors that when I multiply by a specific matrix, I will actually get a multiple, meaning I'll get a vector going in the same direction. And so those are called eigenvectors. They're specific to a matrix. So like this eigenvector 2, 1 is specific to the matrix 1, 2, -4, -1, 4. When I multiply the 2, I get a multiple, in this case 2 times that vector. So I'll get a vector going in the same direction, which in general, again, doesn't happen for just about any other vector in this specific case. So these are called eigenvectors. And again, they go with a matrix. So a matrix will have certain eigenvectors that when I take that matrix and multiply by those eigenvectors, I'll get new vectors going in the same direction, parallel, multiples of each other. Okay, so it basically just means if we multiply an eigenvector by x, I will just get a multiple of x. Okay, doing that matrix multiplication, I will literally get a scalar times the x that I had started with. So here I got 2 times my x value. We call the multiple an eigenvalue. It's denoted with a lambda. And then the x itself is an eigenvector. So here, the vector 2, 1 was our eigenvector. The constant, just a scalar, 2 is our eigenvalue. And they kind of go together. That I know if I take this matrix and I multiply by this vector, I'll get 2 times that vector. Okay, and that's not necessarily the only one. And again, that doesn't work with all. Not 2, 1 isn't some magical vector that will do that with every matrix. It will do it with this matrix and maybe some other ones, but not all matrices. Okay, and in fact, this specific matrix has 2 eigenvectors and 2 eigenvalues. So 2, 1 was one of them that I kind of showed graphically there. 1, 1 is actually another one for this specific matrix. 1, 1 is an eigenvector. Notice if I multiply the matrix times 1, 1, I get 3, 3, which is a multiple of 1, 1. It's going in the same direction as 1, 1. It's parallel to 1, 1. And really, pretty much all 2x2s will have 2 eigenvalues, 2 eigenvectors. 3x3s will have 3 eigenvalues, 3 eigenvectors, and so on. They only exist for squares. We don't have eigenvectors for rectangular matrices. So that really only happens with squares, but you will get 2 for a 2x2, 3 for a 3x3, 4 for a 4x4, and so on. The main kind of exception might be these are going to come from polynomials, roots of polynomials. If we have a repeated root, you would treat that like 2 different eigenvalues. So if I had a root and I got a 2, and a 3 for my roots of a cubic function, those 2's would count for 2 different ones, even though they're the same number. But generally, you'll have 2 for a 2x2, and that'll be most of our examples will be 2x2s because it comes from a polynomial, and we can pretty easily find the roots of a quadratic. But a cubic or above in order, that becomes harder for us to find like quickly. So we won't do a ton of those. But again, you should be able to see how you do that. The main property that we will use with eigenvalues and eigenvectors is it makes multiplying matrices many times a lot faster. So notice here, if I took what I just did, I have a times x. So I have that matrix times 2, 1 gave me 4, 2. If I multiply by a again, I get 8, 4, which is 2 times 2 times 2, 1. Okay, and then if I multiply by a again, I get 16, 8, which is 2 times 2 times 2 times 2, 1. And so you should be able to see that if I multiplied by a again, I would just multiply the vector by 2 again. Okay, and that would just keep on happening if I kept multiplying by a. The eigenvector really doesn't change. It's still 2, 1. The eigenvalue changes in that if I did a times a, I would take the eigenvalue for a times a would be 2 times 2. For a times a times a, it would be 2 times 2 times 2. So my eigenvalue will grow, but my eigenvector will stay the same. And so we can turn matrix multiplication, right? Multiplying a 3 times is a bunch of dot products. Rows times columns, rows times columns, rows times columns, rows times columns. if I can kind of boil it down to doing just 2 times 2 times 2 times 2, 1, this 2 times 2 times 2 is going to be an easier multiplication than a times a times a times a, right? So it makes this multiplying by a matrix multiple times. We can almost turn that into a scalar multiplication instead of a matrix multiplication. And we'll get to why we might want to multiply a matrix by itself multiple times. But most of the applications are, you can do modeling with a matrix. So think like population models or economic models. And so think if you were having something that was like migration, and you wanted to see like a migration model, and you wanted to see over the next 10 years what's going to happen, you would multiply that model 10 times. Or if you had a population growth model and you wanted to see what's going to happen over the next 100 years, you would multiply that population model 100 times, okay? Or however many times it compounds. If it was monthly, you'd do even more or whatever. So that's kind of where we're heading with why we might want to multiply a matrix by itself 1,000 times. It's going to be much easier to do 2 to the 1,000th than a times a times a times a times a times a 1,000 times. Okay, still 2 to the 1,000th. You know, you may not know that off the top of your head, but it's going to be much easier for you to figure out than multiplying matrices together 1,000 times. All right, so 2 main things to notice. If you square a, the eigenvectors won't change. So once I found the eigenvectors of a, the eigenvectors of a squared, a cubed, a to the 5th, a to the 10th, a to the 1,000th are the same. But the eigenvalues do change. Okay, they'll be raised to the same power. So I'm saying squared here, but that really is true for all powers, not just squaring. So for example, if I want the eigenvalues and vectors of a to the 10th, the eigenvalues will be my original values to the 10th. And the eigenvectors will just be the original eigenvectors. They won't change. And that's true to any power. So a to the nth, it would be a's eigenvalues to the nth. Oops. And just a's eigenvectors. So again, it's nice because those are scalars, those eigenvalues. They're scalars. So you're just multiplying a bunch of scalars as opposed to vectors or matrices, which is much less like computationally difficult to do. All right, so I mentioned this, most 2x2s will have 2 independent eigenvectors. You know, there's exceptions like 0, 0, 0, 0. The matrix doesn't really fit this pattern very well, but most matrices will have 2 independent eigenvectors and 2 different eigenvalues. The different eigenvalues, again, they could be repeated roots, so they may not always be different, but independent eigenvectors should happen. Okay, this means that they will be a basis for R2, because remember, if we have 2 independent 2-dimensional vectors, we'll have a basis for R2. In a 3x3, we'd have the same thing. We'd end up with 3-dimensional vectors that are all independent, so they would make a basis for R3 and so on, okay, all the way however big the matrix gets. Its eigenvectors will make a basis for whatever n is. Which means we can express other vectors as linear combinations of the eigenvectors. So if I just have some random vector, I should be able to express that as some multiple of one eigenvector plus some multiple of the other. If those eigenvectors are a basis for R2, they span all of R2, meaning every vector in R2 is a linear combination of those. Okay, or again, R3 if you had a 3x3 or whatever. Which means if I wanted to do a times a times a times a times a times v, it's actually going to be easier to do a times a times a times a times a, oops, times the linear combination of the eigenvectors. Because when we do this multiplication here, it's going to be scalar multiplication, not matrix multiplication that we're actually going to be end up doing. So that's the real benefit of eigenvectors, is it allows us to multiply a lot of times without doing massive matrix multiplication. it ends up being scalar multiplication that we're doing instead. Okay, and you'll see one of these in your homework, and we'll eventually get to what this is. This is a specific type of matrix. It's got decimals in it, so you may want a 4-function calculator if you're going to have to work with decimals. But this is a population model matrix. You can tell because the columns add up to 1. So think of those as percentages. Okay, and the columns will add up to 100% here. Right now, we're not going to put any context on it because I don't really want to overload it. But that's, again, why we're looking at a matrix like this, is this will have an application to it. So we haven't gone over how to find eigenvalues and vectors yet. So for this one, I'm just going to give them to you. The eigenvectors are 0.75 and 0.25, and then 1, -1. The eigenvalues are 1 and 0.6. So notice we could take another vector and just write it as a linear combination of eigenvectors. And for a 2x2, this is a fairly simple little system of equations, right? We're just trying to figure out what multiple of 0.75, 0.25 plus what multiple of 1, -1 can give me 0.9, 0.1. Okay, this is a 2x2 system of equations. So literally, like, this is algebra 1. So again, we've done things you could solve this system. You've really done it even in algebra 1 to solve a system like this. You could do substitution, elimination, whatever. Okay, you guys should be able to solve that system of equations. So I'm not going to spend time doing it. C1 would be 1 and C2 would be 0.15. So if we want to do a to the 5th times 0.9.1, which again, that's a times a times a times a times a. That's what a to the 5th means. So we're just multiplying the matrix A by itself 5 times using matrix multiplication. It's actually going to be easier to do it as multiplying by this linear combination. Okay, a to the 5th times 0.9, 0.1 will be our first eigenvalue also to the 5th. So that was 1 to the 5th. And then we'll have a C. Okay, our C1 is also 1 times our eigenvector 0.75, 0.25. Plus our next eigenvalue to the 5th times the 0.15 times the 1, -1. Okay, so where these numbers are coming from, this is my eigenvalue, my first multiple, and then my eigenvector. And then I've got my other eigenvalue and other multiple and other eigenvector. So this part, if I add those together, those are just, that's just the 0.9.1. So we kind of use distribution and stuff. This is what you're going to get. So again, instead of doing matrix multiplication 5 times, we raise 1 to the 5th, which is really easy. 0.6 to the 5th, again, you may need a 4-function calculator to figure out what that is. But then that's really the main multiplication you have to do, and you just add those numbers together. So this should be fairly easy with like a 4-function calculator where a times a times a times a times a. It's going to take you some time and take you some, it'd probably take you a calculator too, since there are a bunch of decimals. And it'd take you a lot of space. So here we can kind of, again, do this multiplication as a few scalar multiplications instead of matrix multiplications. The more times you have to multiply a, the much easier this is. Like if I had to do a to the 100th, you could either multiply a matrix by itself 100 times, doing 100 matrix multiplications, or we could raise 1 to the 100th, which is 1, and 0.6 to the 100th, which is going to be a very small number, but I don't know what it is. Okay, with these specific ones, you should start to notice, because that's going to start being questions that you'll see, is as I'm raising it to a higher and higher power, this one's going to get smaller, right? 0.6 to the 1,000th to the millionth, whatever, that's going to get very small. This one's not going to change size because 1 to the 1,000th, 1 to the millionth. So we'll actually see that again as we get to what exactly this matrix is. For right now, we're just focusing on what is an eigenvector, what is an eigenvalue, and kind of how can I use it basics. Okay, so this allows us to do large numbers of matrix multiplications as a scalar multiplication instead. So here, if I want to do this to the nth times some vector, I'm going to do my eigenvalue to the nth. And everything else you kind of leave the same. Okay, where C2, X1 and C2, X2, that's just my linear combination that gives me V. So like on this one, we'd have our eigenvalues 1 and 0.6. We'd have whatever we found C1 and C2 to be. Plug that stuff in. The eigenvectors don't change, which is nice because that would be the thing that would be annoying to have to multiply because those are vectors and you have to figure out what to do there. But they stay the same. So it becomes just a scalar multiplication problem. Okay, as far as finding eigenvalues and eigenvectors, for eigenvalues, we find the determinant of A minus lambda I. Lambda I is just the identity matrix multiplied by lambda. So, it's going to be an identity matrix, but with lambdas on the main diagonal. The only reason we can do that is I need to be able to subtract. And I can't subtract a scalar from a matrix, but I can subtract a scalar times a matrix from another matrix. The eigenvectors make up the null space of A minus lambda I times X. Or I guess A times just this. I guess I should have put that there. Which means we want A minus lambda I X equals 0 is what we'll be looking for the eigenvectors. Okay, that's coming from the fact that we're looking for vectors where A times X is a multiple of X. Which is the same as saying lambda times I times X, right? I times X is just X. But using associative rules, I could also multiply lambda times I times X. And then if we subtract it from both sides, we're looking for AX minus lambda times I times X equals 0. And then if we factor out the X, that's what we're really looking for. If we're looking for A times X to just be a multiple of X, we want A minus lambda I times X to give me 0. So that's where that formula is coming from. And so that's how we find our eigenvalues and our eigenvectors. Remember, the eigenvector is the null space, meaning multiples of the eigenvector work too. Right? If I find an eigenvector is 1, 1, 2, 2 will also work, or 3, 3, or -1, -1 will work. Any multiple of it will be essentially like the same eigenvector. So we're looking for independent ones. So don't give two that are just multiples of each other. You need two different ones when you're looking for eigenvectors. Okay. So again, most of our things will be 2x2s, maybe some easy 3x3s or 4x4s. If there's lots of zeros, notice we're doing a determinant here to find eigenvalues. So usually we'll have to do something very simple when it gets large to make sure that determinant doesn't become too difficult. Usually that means having a lot of zeros. So I would find the eigenvalues first. All we're going to do is we're going to subtract a lambda along the main diagonal. And then find the determinant. This should give me a polynomial. Okay, for a 2 by 2, it should give me a second order polynomial. For a 3 by 3, a third order. For a 4 by 4, a fourth order polynomial. Okay, so if I multiply, I can use my shortcut for 2 by 2s to do my determinant here. I'm trying to find where the determinant is 0. So then I multiply this out and I have 4 minus 5 lambda plus lambda squared minus 4 equals 0. In this particular one, my 4 and my 4 will cancel and I have something I can factor. Most of the time, our stuff will probably have chosen ones that can factor. Eigenvalues don't have to be integers. We saw that in that example with all the decimals. It won't always be integers, which means you can't always factor. But you can use things like the quadratic equation or whatever to also get those eigenvalues. This one's we can factor. So I have lambda times lambda minus 5 equals 0. So I have my two eigenvalues 0 and 5. Oops. That's like lambda 1 is 0. Lambda 2 is 5. Okay, then to find the eigenvectors, we plug those in to the 1 minus lambda 2, 2, 4 minus lambda. So I actually subtract 0 along the main diagonal, which obviously in this case, since it's a 0, it doesn't matter. But I would subtract that eigenvalue. And we're trying to find the null space. So basically that times x equals 0. We've been doing this since January. Okay, use whatever it is that you want to use to figure out what is the null space. For 2 by 2s, at this point, most of these should be ones you almost could do in your head. So if we look at this, I'm looking for something times 1 plus something times 2 to be 0. And then that same something times 2 plus something times 4 gives me 0. So like 2, negative 1, right? 2 times 1 plus a negative 1 times 2. 2 times 2 plus a negative 1 times 4. If you don't see it, solve for the null space. That is, again, we've been doing that since very early in the semester. Find the null space. And it's a 2 by 2 for pretty much most of what we're doing. So that shouldn't be too terribly difficult. Okay, then I'm going to do the same thing for 5. So I'm going to do 1 minus 5, 2, 2, and 4 minus 5. And figure out what I would multiply by that to get 0. So here I have negative 4, 2, and then 2, negative 1. And again, lots of them will be ones that you should hopefully be able to see because they'll be integers and stuff. It's not always the case. Okay, if you have to solve it, go ahead and do elimination or whatever you want to do. Find the pivots, find the free variables, all that stuff. Here, again, I can see that if I multiply by 1, 2, I'll have a negative 4 plus 4 and a 2 plus a negative 2, which will both give me 0. Any multiple of those would have also worked, right? For 2, negative 1, I could have done negative 2, 1, or I could have done 100, negative 50. Those are all fine. Okay, but those aren't two different ones. So what I mean by different, they should be two independent ones. So don't give me 2, negative 1, and 4, negative 2. Those are both for the same eigenvalue. You want a different one for the other eigenvalue. And in general, I would simplify it. Make it as like reduced integer as you can. There's no reason to use 100, negative 50 if the whole point is to make our calculations simple. Make that as small as possible. Your eigenvalue can kind of absorb the big multiplications instead of putting them into the vector. Okay, careful because elimination changes lambda. So we do a lot of elimination. with a lot of the different things we've done. And certain things don't change, like the determinant and the column space, or the row space and the null space, and all that stuff doesn't change. Eigenvalues will. So like here, if we found the eigenvalues of A, okay, we're going to get 1 minus 2 lambda plus lambda squared minus 1 equals 0. So we'll have lambda times lambda minus 2 is 0. And so we'll have two eigenvalues, 2 and 0. And again, it doesn't matter which one you call lambda 1 and lambda 2. If you do 2 and 0 or 0 and 2, it doesn't really matter. You just want to make sure that you're coming up with an eigenvector that goes with 0 and one that goes with 2, and don't switch those, because those do need to kind of be matched together. Okay, and then here I also have U, which is just the eliminated form of A, right? To do elimination, I just add row 1. And that'll eliminate the second row completely. And we'd have U over here. Well, if I go and I find the eigenvalues of U, here I'll end up with a negative lambda plus a lambda squared minus 0. So I have lambda times lambda minus 1 is 0. So I have eigenvalues 0, oops, and 1. Okay, not the same, right? I did elimination and they changed. But one thing that is nice, if your matrix is triangular, the eigenvalues are the diagonal entries. Okay, notice here it was 1, 0, and that's what we got here was 1, 0. That'll always happen. So if you have a triangular matrix, you can just take the numbers off the diagonal. Those will be your eigenvalues. You don't have to do the subtracting, find the determinant, and all that stuff. Okay, and that really should make sense if you think about how we find the determinant of a diagonal or triangular matrix. And what we're really going to be doing there is should make sense why that's going to happen. But again, if I do elimination to get a triangular matrix, it will not be those entries. Okay, it's only if I'm already looking at a triangular matrix. It's just the main diagonal entries. Those are my eigenvalues. So that's another one where we could see a larger one. Or if I was like, what are the eigenvalues of this 3 by 3 or a 4 by 4 or 5 by 5? Well, then this it's 1, 4, and 6. Okay, and then we could find the eigenvectors. We can find the null space of a 3 by 3. That's not beyond what you guys should be capable of at this point. It's mainly the eigenvalue part that gets difficult as it gets large, because it's finding a determinant. You'll end up with a polynomial. If it's a 4th order polynomial, it can be hard to find the roots without a calculator or something. Okay, some other things that can be helpful. The product of the eigenvalues is equal to the determinant. So if I know the determinant, I know what the product of the eigenvalues should be. If I know the eigenvalues, I can find the determinant by just multiplying what I've got. What I find most useful is the second one, because that one's easier to do. We don't always know the determinant. It's not always easy to find the determinant. But what we call the trace of A, just adding the numbers on the diagonal, which we could always do, that's really easy. That's the same as the sum of the eigenvalues. So I use this a lot to catch if I've made any mistakes. Add up the eigenvalues, add up the numbers on the main diagonal, they should be the same. Yeah.
Is that true for triangular and multiple?
Yeah, it's true for all of them. They won't be the same numbers, but they will add up to the same numbers. In a triangular matrix, they will be the same numbers. But in other matrices, they'll just add up to the same thing. So yes, that's true of all matrices, is that if I add up the main diagonal entries, it will be the same as if I added up the eigenvalues. And so again, that's a really easy way to check your answers. You just add up the eigenvalues you got, add up the diagonal, and if you get different numbers, something went wrong. Okay, if a matrix is singular, which again, singular means the determinant is 0, or that the inverse doesn't exist, or the rows are not independent, the columns are not independent, there are free variables, all that stuff comes from the same thing. 0 will be one of the eigenvalues. It should be most obvious because if the determinant is 0 and the determinant is the product of the eigenvalues, it means one of them should have had to be 0. It doesn't mean they're all 0. It means at least one of the eigenvalues was 0 if you've got a singular matrix. So this is, again, it's a really useful thing for 2x2s. If I have like 1, 2, 2, 4, okay, singular matrix, right? Determinant is 0. There is no one of the rows are dependent. There is no inverse, all that stuff. If I'm looking at this and I want eigenvalues for this thing, I could say, well, it's singular, meaning one of the eigenvalues has to be 0. And then I know the trace is 1 plus 4, which is 5. Well, if one of the eigenvalues is 0, the trace is 5, and the eigenvalues have to add up to 5, this means the other eigenvalue is 5. Right? I can use these things to kind of take a little shortcut on certain ones where I'm not having to find a determinant, solve a quadratic, any of that stuff. I can just say, well, this thing's singular. One of the eigenvalues is 0. I can use then the trace to find the other in a 2x2. In a 3x3, that might help you narrow it down, but you won't be able to figure it out because there's 2 other ones to find, have to add up to 5 if this was 3x3. Okay, so find the eigenvalues and eigenvectors. So I would first think, is it triangular? It's not. If it was, that's a shortcut that you should use. Is it singular? It's not, because the determinant is 8, right? 5 minus a negative 3 is 8. So I would think of those types of things first so you're not doing extra work. Here, this one is not. So we have to kind of do the full steps. So we'll have 5 minus lambda, negative 3, 1, and 1 minus lambda. So this is 5 minus 6 lambda plus lambda squared minus a negative 3, so plus 3 equals 0. So we have lambda squared minus 6 lambda plus 8, which means we'll have lambda minus 2 times lambda minus 4 equals 0. Okay, that one can be factored. Again, if it can't be factored, it does not mean there's no answer. It just means the answer is not integers. So you could use like the quadratic formula or something like that. In that case, I'm fine with you using a calculator. But in general, if it can be factored, make sure you can factor. A couple of people on the last test didn't seem to be able to factor. All right, so we have one eigenvalue of 2. For its eigenvector, I'm just going to subtract 2 along the main diagonal. So I'll have 5 minus 2 is 3. And then 1 minus 2 is negative 1. And then I'm going to look for the null space. Basically, what vector would I multiply there to get 0? And again, if it's obvious, use it. I don't need you to do a bunch of extra work here. You hopefully could see that 1, 1 is an eigenvector here. 3 plus a negative 3 and 1 plus a negative 1 will both be 0. If it's not obvious, go ahead and do whatever work you need to do to figure out that null space. For the second eigenvalue, I'm going to use 4. And again, subtract that along the main diagonal. I get 1 and a negative 3 and 1 and a negative 3. So my second one is something like 3 and 1. Okay, and again, other multiples of that would work, right? You could do 1 and a third if you wanted to, would also work. I would use kind of the most reduced integer one you can do because it's going to make the rest of it probably easier if you don't use things like 30 and 10 or 9 and 3 or something. Go ahead and kind of take the smallest multiple with integer values, and that's probably going to be the easiest one. But you don't have to. You can use other things. Okay, and then it says use a property to check your work. So you could do something like the trace. It's just the sum of the diagonal entries. So the trace here is 5 plus 1, which is 6. And then notice that my eigenvalues 2 and 4 also add up to 6. These should be the same. That's really the easiest one to do. Add up the diagonals, add up what you got. If they're not the same, something's wrong. If you have time, that would be something to go back and try and figure out where a mistake happened. The other one with the 2 by 2 is not that difficult either. We can find the determinant of B, right? It's 5 minus a negative 3, which is 8. That should be the same as the product of the eigenvalues, which ours is 2 times 4, which is also 8. Those should be the same. So either one of those will work. In 2 by 2s, you should also be able to see there's a system of equations there you could use to find the eigenvalues in a 2 by 2, right? We could do the trace equals lambda 1 plus lambda 2, and the determinant equals lambda 1 times lambda 2. So if I know these two numbers, I have a system of equations there I could also use. In a 3 by 3, you don't, because you need a third equation, which we don't have. But that's another kind of, I don't know if it's a shortcut, because I don't think the 2 by 2s are that hard to solve, but you can. All right, if you guys have questions, we have close to 10 minutes left. If you don't, tomorrow's also a good day to ask questions as you guys start working on the problem set and seeing things that are making sense and things that are not. Tomorrow's a good day for that. Problem sets due Friday. Then you have spring break, nothing to do, hopefully. And then we'll deal with the rest of the lessons when we come back. So if you guys have questions, let me know. If you don't, you guys have a good rest of your day, and I'll see you guys tomorrow for a quick check-in.
Thank you.
Uh-huh.
Thank you. Could you go to the slide that says 1